What's up, algebra? Today we are moving on to 7.7, which is exponential growth and decay. Okay, so we're still looking at exponential functions, but now we're looking at a pretty big real-world concept, or I guess application of it. So this is used a lot with finance. When you get into like personal finance, if any of you decide to go into like business sort of professions, you'll see a lot of this sort of stuff. So for that reason, I think it's kind of cool that you guys get to learn it. So we'll just go ahead and jump into it. Okay, so first off, we have exponential growth. Okay, and exponential growth is that same kind of form that we saw previously in 7.6. So we have a times b to the x. Okay, so again, our exponent is our variable. That's what makes it exponential. Okay, and then b is always going to be greater than 1 whenever we have exponential growth. Okay, and then also b is called our growth factor. Okay, pretty much that is 1 plus the percent rate that we're having, or percent rate of change, I guess you would say. So yeah, we'll get into that as we go into some examples though. All right, so for problem 1, this is on page 461. It says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. Okay, so right away you can see that this is a pretty real world sort of concept that we are covering here. So problem A asks, if the trend continues, how much will be spent at restaurants in 2015? Okay, so, whoops, that's the highlighter. We do not want that. So first of all, we want to start out with that same equation we had earlier on, which is y equals a times b to the x. Okay, x is our number of years since 2005. Y is the amount spent at restaurants. Okay, that's what we're trying to find. A is going to be the initial amount spent. Okay, notice they're doing this in billions of dollars. Okay, so that we don't have to work with the actual billions. So that'll be 360. And then B is our growth factor, which is 1 plus 0.07. That 0.07 comes from the 7% that we have up here. Okay, so like I said, we add 1 to whatever that rate of growth is, and that will give us our growth rate, I guess you could say, our growth factor, I mean. Okay, so if we go ahead and write that out, we have y equals 360 times 1.07 to the power of 10. Okay, because we're trying to figure out 2015, so that'll be 10 years down the line. Okay, so we can go ahead and just type that into your calculator. Okay, when you do that, you should get around 708, so that would be $708 billion. Okay, and that is it for for problem 1, part A. All right, so if you've got a good grip on that problem, go ahead and go through got it problem 1 right here. Do that one on your own, pause the video, see if you can get it, and then after that, we will go ahead and move on. Okay, so I said earlier, this is a really good example of real world applications of math. Okay, and you'll see that a lot when you get older with compound interest. Okay, so when you open up a bank account of your own, you'll see this term compound interest pop up. So this is kind of what it is. Compound interest is really, it's an example of exponential growth. And then we're going to go ahead and look here on page 462 at how compound interest works. Okay, so I am going to just highlight this equation right here. Okay, I would put this stuff into your notes. Okay, so in this equation, A is your balance. Okay, so like if we were doing, I did it again. If we were doing like y equals mx plus b, just a standard equation, typically we're going to be looking for the y value because we're going to have these three if we're able to solve it. Okay, so y is kind of, or a is kind of our y for this equation in that way. Okay, so a is our balance, p is the principal. Principal just means the initial deposit. Okay, r is the annual interest rate, okay, which will be expressed as a decimal. N is the number of times interest is compounded per year. And then T is the time in years, okay? And that's really how those, or how compound interest is calculated. So make sure, again, you get all of this stuff written down. Make sure you get the equation and all of that I just put in that box. All right, so if we look at problem 2, we can kind of see an example of compound interest. So it says, suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? Okay, so there's a lot of different things that we need from, I guess, this example, right? So we need our $2,000, right? We need our 4.5% interest, and we need to know that it's compounded quarterly, okay? And then lastly, we need to know what it will be after 18 years, okay? So I'm going to go ahead and write out my equation. So we have A equals P times 1 plus R over N, and then that will all be to the power of N times T. Okay, so A is what we're trying to figure out, like I said earlier, so we don't know that yet. Okay, P is going to be our principal, which is $2,000. That was our initial deposit. Okay, then we have 1 stays the same. The R, we have our interest rate. Okay, it's 4.5%, which if we put into decimal form would be 0.045. Okay, and then that will be over N, and N is our number of times that it's compounded per year. It's compounded 4 times per year, right? That's what that quarterly means up here. Okay, so we're going to put 4 in the denominator there. And then from there, we'll go ahead and use that same 4 up here in the exponent, and that will be multiplied by our number of years, or the time passed, which would be 18 years. Okay, so yeah, that's our equation, right? So really the hard part here is setting it up, and then the rest you can just type into your calculator. Okay, I'm personally going to put this, and then I'm just going to leave this for now just to make it a little bit easier on myself. I'm going to do 4 times 18, which will give me 72. Then I would type this part into my calculator. Okay, so that will give me 2,000 times 1.01125. I was just reading that from the book there, so you're not expected to be able to do that quickly. And then still to the power of 72. And then that will give you that A, when you type that into your calculator, your new balance after 18 years would be $4,475.53. That's after 18 years, okay? So you can see there we over doubled the amount of money in the account, which is pretty good. All right. Okay, so I want you to go ahead and do Got It Problem 2. It uses the same problem as this stuff up here. There's just one thing that you're changing. So your job really is to find out what is changing there, and then make sure you can enter all that into your calculator and get what you need to get for your solution for this problem. All right, so our next thing that we're looking at, and really our final thing, is exponential decay. Okay, exponential decay is going to be sort of the same thing as exponential growth. Okay, the difference is that when we have y equals a times b to the x, this time b will be between 0 and 1. Okay, so yeah, it's a little bit different from exponential growth, right? Because growth, b was greater than 1. Now b is going to be less than 1, but it's still going to be a positive number. All right. And then again, similar to our growth factor, we now have a decay factor, which again is still b. Okay. And that'll be 1 minus the percent rate of change that's going to be given to us as a decimal. All right. So let's go ahead and look at an example of this. All right, so problem 3 is a good example of exponential decay. It says the kilopascal is a unit of measure for atmospheric pressure. I don't know if I'm pronouncing that right, by the way. I've never heard of that. Okay, but it says the atmospheric pressure at sea level is about 101 kilopascals. One of those, I don't know. For every 1,000 meters increased in altitude, the pressure decreases about 11.5%. What is the approximate pressure at an altitude of 3,000 meters? Okay, so we're going to set it up the same way. That's 3 times now I've done that. I feel like a fool. So we'll go ahead and set it up. Y equals a times b to the x. Okay, and then we will go ahead and write out the stuff that we know. Okay, so y we're trying to find. Okay, a is our initial value. Okay, that would be 101. Okay, b is then going to be our growth or decay factor. We know this one is decay. One big way that we can tell if it doesn't tell us if a problem is going to be exponential growth or exponential decay would be this right here, right? So this is telling us that the pressure is decreasing. Whenever it's decreasing, we can pretty much know for sure that's going to be decay, right? Because it's going to be going down. All right. So it's going down by 11.5%. Now, in order to get the number that goes there, I am going to do 1 minus 0. And it's going to be 11%, right? Which would be 0.115. Okay, and that will give you 0.885. All right, so that's the number that goes in that blank. I'm going to go ahead and erase the blank. So we have 0.885. All right, and then from there we have our x, which will be the number of times basically that we're going down. All right. So we have 1,000 here. That is 1 unit, right? Every 1,000 meters is 1 unit. Okay, and we're going a total of 3,000, so that would be 3 units. Okay, because of that, we want to put a 3 in place of our x. Okay, and then from here again, we're just putting that in the calculator. All right, when I do that, I'm going to get about 70. All right. Now notice that one is a lower value than our initial value, whereas a growth factor would be a greater number than our initial value. All right. Okay, so the last thing that I want you to do is just go ahead and do Got It Problem 3A. Again, it's just going to look at this problem. You're just changing one of your values, and then after you do that, that is going to be it for this video. So that's great timing right there, huh? I will see you guys next time in class.